Hi everyone. Today we have Yichi Zhang, and Yichi is a postdoc associate at the Diverge Institute at UNS. He is hosted by David Knock and Levan Zhang. Prior to this position, he received a PhD from University of Michigan and other advised by National Foundation. His research is interdisciplinary. He uses information science, computer science, operational research, artificial intelligence to build foundations for trustworthy and socially aligned decision AI plans. His work has appeared at leading venues like Moonips, IEEE, EC, and he's a co-organizer of workshop on incentives in academia. Fostering cross-disciplinary dialogue on incentive design and information integrity in scientific systems. Today, he's going to tell us about his work about alignment of integrated data, incentives, and application.
Cool. Thanks for the nice introduction. And can everyone hear me is okay? From Zoom? Yeah, let me know if there's a problem of hearing me. If not, then I'm very happy to be here to share my recent progress about this nice problem about alignment from imperfect data. And I'm going to show you my perspective about this problem and what is this problem about. Okay. So the goal of AI alignment was to ensure AI to reliably act in a way that is aligned with human values or human intents. And this term was first proposed by OpenAI to design ChatGPT, and it has been the very secret magic of the success of ChatGPT. So how it works? So we're going to collect human data as an annotation of whether a human prefer two responses from the same question generated by a language model, and then human will select which one is preferred over the other one. And this preference data is used to train AI policy to generate the preferred data with higher probability in the future. And this is closely aligned with this pipeline where we have a human contributed data, which is used to train AI or policy and leads to some desired outcomes. It turns out that this is a very important problem, and recently there has been a lot of government investments and fundings about this AI alignment project. Another example is Redis has been making over $200 million just by selling this data to Google and OpenAI primarily for alignment. Another example is OpenAI's ex-co-founder has been start a startup directly about the safety alignment of AI. In spite of the success of ChatGPT and the many other AI alignment problems, there's still a lot of issues within this pipeline that can cause misalignment. And what I mean by misalignment is that under misaligned policy, the achieved outcome might be systematically diverge from the intended outcomes. And there might be many different reasons for this. Let me briefly walk through a couple of them. So at the human level, human contributor, data producers' incentives might be different from the data collector or data requesters. On one hand, producers aim to maximize reward with minimal effort, but requesters only care about data quality. So one example of this can go wrong is when we align the language models with a bias and a low effort preference data. And for example, when the annotator is not paying attention to the annotation task, he may prefer some superficial information. For example, whether answer A is longer than answer B. And it's going to bias against this longer answer. And directly training on this data will reinforce this preference bias and making the AI to generate more superficial and longer context, which is not actually aligned with human preference. So what we need here, which we refer to as incentive alignment, is to design a mechanism that provides a reward to incentivize high effort from human. Another level is about data. So when we collect data and face a data set, the issue here is that we don't really know what's the quality of the data, like especially the data contributor. And this problem has been more troublesome when AI is taking the role of data producers nowadays. And there's a well-known kind of example called the mad cow disease of AI, basically saying that when we feed AI itself with a lot of AI-generated data, it's gonna, after a couple iterations, the AI is gonna generate a lot of nonsense. So it's really concerning that we directly trust an unreliable AI data. So here, what we need is an evaluator that it can reliably evaluate or assess the desired information within the data set. The last layer about decision level. So this directly speaks with the decision policy. When the decision policy is making decision, well, assuming the data is perfect, but at the end of what is not, then the policy might bias and leads to a misaligned outcome. So here, the design goal is to make the decision or AI policy be aware of the data quality, and in particular, the noise, the bias, or strategic reporting of the data. Okay. Before I run into my own research, let me just say a little bit more about this data to decision pipeline. And it actually works way beyond just AI alignment or preference alignment. So for example, in recommender systems, we collect users' feedback about ratings or lacks of the different content, and then the recommender algorithm is trained on this feedback and aims to provide higher quality content to the users. Another example in this pipeline is peer review, where reviewers contribute potentially noisy reviews, and the conference has to make decisions of whether to accept this paper or not based on these noisy reviews. And here the outcome will be the acceptance of the paper. Okay, so there are many aspects of the problem, very broad problem. But my perspective here is to focus on the data quality. So a key issue within this misalignment pipeline is that we don't really know the information within the data. So in this talk, I'm going to show you how to design information evaluator that on one hand can be mapped as a reward to incentivize human with a carefully designed incentive mechanism. On the other hand, it can also be used to evaluate data contributors or data producers, which in turn going to inform the downstream decision policy making. A couple key properties that we want from this evaluator is that first, it has to be very scalable. So we don't really want to, for example, assign an expert to each of the data point and take a look at it and trust the expert on every data point. We want an automatic evaluator that can be highly scalable. And second, which is kind of important, is that we need the evaluator to be manipulation resistant. This means that when we are evaluating human and they have strategic incentives to game the evaluator or game the mechanism, so we don't really want them to exert low effort, but also obtain a very high score under this evaluator. It's actually a very important problem for a lot of data evaluation pipelines. Okay, so in this talk, I'm going to walk through the 3 steps: incentive alignment, quality alignment, and policy alignment, an issue with one project. And for each of this, I'm going to focus on slightly lower level problem. So for example, for incentive alignment, my focus will be on incentivizing human effort under a AI contamination problem. And for example, in the quality alignment, I'm going to focus on how to use language model as a tool to evaluate information. And for policy alignment, I will discuss about peer reviews and how to make decisions under noisy peer reviews. Okay, feel free to raise any question during the talk. And if no question, then I will proceed to the first part. Okay, so let's talk about incentive alignment. And here, I'm going to focus on one problem called AI contamination and how to preserve human effort in this problem. Okay, so what does that mean? Let me first introduce this new rule of AI within this data to decision pipeline. So right now, AI can serve both as data producers as well as evaluators. For example, right now we are not using RHF anymore. So like reinforcement learning from human feedback is a kind of old story. People usually use AI preference label to train AI. Another example is language model as a judge. So basically, we are using language model to evaluate other language models training and supervise the development of other AI systems. So because it's very important role of AI, it's really important to guarantee that they are doing their jobs. So there are many new challenges and also opportunities. Let me focus on one of them, which is called AI contamination. So what happens here is that when we collect data from human, and we assume this data are actually human effort or human values, but it could be a case that a fraction of human agents are actually using AI to generate data on their behalf. And secretly, you don't notice because when you're asking them to just submit something, all you observe is their submitted data. So this can be very troublesome because when we have an AI contaminated data, which is mixed between human and AI, directly trusting this data to make any decision or train an AI policy will lead to bias, as the Matt Call example we chat about. Even worse, this is actually pretty common. So there have been studies showing crowdsourcing workers are actually using AI very frequently on tasks like summarization. And in peer review, a lot of reviews have been shown to be substantially modified by language models. Okay, so what we need here is the key problem is incentive. How can we motivate agents to not use AI in a way that if they care about the reward we design for them, is there a way so that if they exert effort and they can maximize the reward, but if they use AI, the reward will decrease? Then the question is, can we design such a mechanism that reflect the desired human effort? What does that mean is like higher effort means higher reward. And also, we also want this mechanism to build without ground truth. Like in a sense, we don't really have to have some experts to take a look at everyone's report. That's very time consuming and sometimes infeasible. Okay. How to do this? There's a technique called peer prediction that offers a very interesting solution. Suppose the data we collect from humans is like a matrix where rows are agents, let's say Alice and Bob, and columns are questions. And we assume that the questions are IID. And Xij will be agent I's response for question J. Peer prediction basically is a mechanism that takes this matrix as input and design a reward for each of the agents. And Cohn and Schoenberg, which is prior work, shows that a lot of these mechanisms are basically estimating the mutual information between agents report. So what is a mutual information? Basically is the mutual information between two random variables, X and Y, is basically the K-out divergence between the joint distribution and their product or marginal distribution. And intuitively, this mutual information is measuring how more often we're going to observe X and Y simultaneously compared with their frequency in the prior. So suppose we're just designing a reward using the mutual information between two agents. For Alice, I'm going to pair Bob with him. And for Bob, I'm going to pair Alice with him. And then in this case, suppose we have a score of 0.7 for this mutual information. Why is this useful? First, as you can see, there's no ground truth in the pipeline, right? So all we need is this matrix of data. Second is incentive aligned in the sense that if anyone, let's say Alice, try to manipulate the response by report X hat instead of X, and there's an arbitrary mapping from X to X hat. And any manipulation will only decrease the mutual information. So by doing so, it's going to decrease the mutual information from 0.7 to 0.5, which is very nice property for this.
So yeah. I have a question about how do you tackle the mutual? I know mutual information when you try to estimate that, and as the dimension become very high, there could be very, very inaccurate. And from classic method could include, like I remember some physics guys, they write mutual information estimation using the nearest neighbor. And in recent years, there are neural network based mutual information estimator. Like I remember the name of the paper, MIE or something like that, right? So how could you control that part? So in the dimension, yeah.
Good question. So here we basically assume this data we collect is a multi-choice response. So X will be, for example, the simplest will be yes or no binary response. So that will be very easy to estimate. But it's a good question for how we're going to compute.
Yeah, but if it become a text or something
Yeah,
very,
exactly.
very long, high dimensional, your estimation could be.
Great question. We're going to chat about that in the second part of the talk.
Okay.
But let's just, for now, assume this is a discrete low dimension information signal. Cool. All right, so we have chatted about this nice property of peer prediction, and just to emphasize that this technique is very important for settings where there's no trusted verification like blockchain, and where humans are very strategic. We try to game other agents to get more benefits. It's very important to verify these two properties of the mutual information technique. Okay, so what is the problem? The problem is about chip signals. Here, let's assume Alice or Bob are not human, but it's using AI on their behalf. And for example, Alice is using AI to modify the signal from X to Z, and then it may mess up the reward in some way. So for example, in this case, it's kind of clear that it can decrease a little bit from 0.7 to 0.6, which is okay because truth telling or report real information is still a better. But what is troublesome about chip signal is that it's very highly correlated. So it's a non-trivial fraction of agents are all using the same chip signal. So for example, Alice and Bob are both using ChatGPT to answer the question. And this response will be highly correlated and even more correlated than the real human signals because AI are trained to be similar and consistent on the answer. So this is really a problem for peer prediction because we don't have ground truth. There's no way we can distinguish from chip signal to the real high effort signal. Okay. So here's the question. Can we design something meaningful so that the reward of the mechanism can only decrease when any one of the agents use a low effort reporting strategy? So here, basically by low effort, what I mean is agents manipulation X hat should be independent of the real signal conditioned on Z. Okay, so let me explain that. So low effort reporting strategies basically assume that agent cannot observe both X and Z on the same question. So they either exert effort obtain X or they decide to cheat and use an AI. So a chip signal can capture, a low effort reporting strategy can basically capture some very common low effort behaviors like report the real signal on some of the questions and use AI to cheat on the other half, or random report on some of the questions, or always report the same thing for all the questions. So those are the strategies we try to avoid. We try to design this reward so that penalize these kind of strategies. Okay, so how to do that? Recall that the chip signal really peer prediction, but the good news is that we can actually, from the requester's point of view, he can also observe some signals about a chip signal. So for example, the requester can also draw some samples from ChatGPT. Suppose all agents are using the same AI, but we do have a discussion later for different AIs. Okay, so then the question is, how are we going to use this requester signal Z bar to design a reward? The idea is to reward agents based on the condition mutual information. Okay, so what is the condition mutual information? So suppose X and XA and XB, which is Alice and Bob signals, are represented by a circle. The common area will be the mutual information between them. The condition mutual information is basically, I'm going to remove the information that is already within Z bar. So intuitively, I'm measuring how much more information the two on top of the information within the AI. And how well this works actually depends on, basically we want this score to be small because both agents are using a chip signal. We want to penalize them by showing that this is actually not a high reward. So how well it works actually depends on how informative Z bar is. So in this example, it's a good case because Z bar has a very high overlapping with all the other cheating signals Z. So the mutual information between ZA and ZB condition on Z bar is actually pretty small. So this case will be very fine. So just one more theoretical insight, and then we'll move on to the results. The theoretical insight is that if we can guarantee the human information between two X, which are two human information, is higher than the conditioned mutual information between two AI, as well as one AI and one human. If we can guarantee that human is the best, human correlation is the highest, then using this mutual information between X, actually this should be X hat, we will maximize the expected score among any low effort reporting. So this means that as long as the true information is larger than the cheating information in any sense, then we can guarantee that any combination of any low effort strategy deviation will only decrease the score. Okay, so how well it looks in practice. Let me show you one example where we have a real crowdsourcing data set, and we can simulate AI signals on that and using the original data as a human signal. Okay. So here is basically the mutual information between a human and an AI, where each group here represent the same AI one AI that generate the requester Z bar, and each color bar within the same group represent the AI that generate a cheating signal. So for example, in this case, this will be the where the requester is using ChatGPT 3.5, and this orange bar will be humans mutual information with another human conditioned on the Z bar being GPT 3.5's information. So what the takeaway from this figure is that the mutual information between a pair of human, which is the yellow bar in every group, is always higher than the mutual information between an AI and a human, especially when Z bar is from the same AI that agents are cheating. So in 3.5, then this yellow bar is smaller than the orange bar group, than the green bar, which is agent are cheating using GPT-4, and I'm also conditioned on GPT-4, is also significantly smaller than the correlation between a pair of average. So this is the positive news that human can actually provide unique information that no tested language model.
So if I understand correctly, you are incentivize the difference, right? To encourage human to have style or things like different from AI, and you find this mutual information.
Yeah.
But I think the efficiency of your method also depends on the context, right? If that's like a math, a physics, or something, then they are correct answer, and they prove the way to prove are limited.
Yeah.
But if you're doing like texting, then could be a good choice, right?
Yeah, exactly. There's there should be some context about how this works. In this problem, we are mostly focusing on subjective tasks, which means our human expertise or the ground truth. In some cases where like math, or there's a real problem with the ground truth answer, sometimes human can be outperformed by AI. AI can be even better than human. In that case, then the condition mutual information between human might be just noise.
Nice.
Right. So yeah, that's a good point. It depends on context.
You say there is a ground truth. What about the subjects that what? You say this is the human, whatever you have.
Yeah.
There's human among the humans, like what? That's like a real issue that is being discussed these days, right? It's like, is this, for example, is AI basis or whatever? Some person may think yes, some person may think no. Like if you give them a sentence, so how would we discuss these issues?
Okay, so like the question is, what if there's no ground truth and the question is subjective, and how does this work? Yeah, as you can see, we are basically estimating the correlation between humans' judgments, and that works independent of the ground truth. So, for example, if two humans both agree that this sentence is toxic, and we basically assume that they have some additional correlation than AI, that means this correlation is basically humans' value, reflecting human value and human diversity.
Some sort of, right.
Yeah. And also, right. Yeah, so this basically works on with no ground truth. But also within the ground truth setting, if you don't observe the ground truth, you can just apply the same method directly, because everything term here are directly observable from the data. Yeah. Cool. I'm gonna skip this slide, but basically this is a curve where we simulate some AI agents and using the area under the curve about different method, then say which method one, which is what we chat about, is a conditioned peer prediction, actually works pretty well. Let me summarize this part by explaining why this is cool. First, as mentioned, this is like verification free, no ground truth is required, and it's manipulation resistant. And some assumptions, like basically no manipulation can improve the score, report the real human information. And lastly, speak about the incentive of human. It kind of discourage human to over-reliant on AI. And this is a very important problem for this human-AI collaboration. When the human knows that his information can be overturned by AI, and how we're going to encourage them to exert their real human effort. Cool. I'm going to pause here for question, and then I move to the second part. Cool. All right, so the second part, we're going to talk about evaluation and how to design an automatic evaluator based on human judgment. And this speaks with the quality alignment. So here, we're not dealing with human anymore. We are dealing with AI and how to evaluate the information about that. But fundamentally, it's sort of like the same task. Before I talk about method, let me ask a question of these two paragraphs are two reviews of the same paper. Can anyone have a guess which one is AI generated?
Feeling the left one.
The left one?
Yeah.
I
mean, the paper is engaging and addresses a highly pertinent issue.
Okay. Any other opinion? Okay. It turns out that the left one is human, and right side is GPT. Yeah, as I can see, it's a little bit hard to say, but if you look at lower level, you can see that the right-hand side is saying something like, well, A and the paper do B, and then might impose some significant challenges. This is pretty superficial information. But the left-hand side is directly saying a problem. Actually, this is a review for our paper. It shows like some concern about the robustness. So by this example, I'm going to motivate a problem that how can we evaluate textual data that are generated by AI agents? And the goal here is to evaluate the real information within the text, not just the superficial information, and how we're going to do that. So let me recall the pipeline here. You have human provide human data, AI contribute AI data, and they both right now they are both serving as a goal for the downstream policy decision making. Our objective here is to design an evaluator primarily focusing on evaluating AI, the reliability of AI. And our goal is to score informative textual feedback. Also, we want this to be verification free, so nobody has to take a look at the one paragraph by one paragraph. Another thing which is pretty problematic is data leakage. And this means that when we design a benchmark to evaluate AI agents, after a couple months, it's going to be learned. There will be new AI models that are already trained on your benchmark to be very good at your benchmark. So this data leakage problem is really troublesome for benchmarking AI or evaluating AI agents. And the key issue here is that we need a consistently refreshed data set, and we don't need the ground truth for it. So as you can see, the idea is still to try to use peer prediction, so that it's a very nice properties that it can evaluate the real information. We care about verification free, and because it's verification free, when there's a new data set, let's just say, for example, peer review, we don't really need ground truth to design an evaluation. We can just directly using different agents review for the same paper as a reference. Okay. So the key challenge here is how to deal with textual data, as mentioned, that is very high dimension. How we're going to measure the mutual information. So the key insight is use language model as a tool. How to make it happen? Suppose we have one item, let's say a paper, and two agents response of the same item, and their paragraph of text. Recall that the idea is to measure the mutual information or between two agents response. So basically, I'm care about how likely I'm going to observe this two paragraph of text for the same item simultaneously, compared with observing them separately from the prior. So let me rewrite this formula here. So basically, this is a log score of the difference between the joint distribution and product or modular distributions. Let me write it in a different way. So it can be understand as the log probability of condition on Alice's review. What is the probability of Bob's review minus the prior of Bob's review? And this is a form that we kind of are happier with, because we can directly prompt a language model to show that, okay, so you are the second reviewer, and here is the reviewer for another review. Here's a review of Alice. Please provide your judgment. And what is nice about this tool is that we can enforce a response. We're going to force the language model to generate a observed response XB, and we can estimate the log probability of so condition on XA, what's the probability of XB, where the probability is basically measured by language model's generation. And basically, language model is the next token predictor, right? So it can use a chain rule to estimate the paragraph of text token by token. Okay. And we can do the same for the second term, which is basically remove everything about XA and directly ask the language model to provide a review XB and what's the probability of that. And then taking the difference, we have this estimation of mutual information. And we just recall that, sorry, question?
Yeah, so do you have any few shot for the prompt?
Any example for the prompt?
Yeah, you have zero shot.
Oh yeah, zero shot.
How to keep the consistency for each response?
How to keep the consistency for each?
Consistency for your response.
What do you mean by consistency here?
You mean temperature, right?
Yeah.
Oh.
But I got your idea. You extract the probability directly, not the. You don't care the exact output, right? You extract log probability.
Yes, exactly. So basically, we take the default temperature and the language model. And what is nice about this is basically we're taking the difference. So there might be some for different model, it might be inconsistent for different examples, but the differences between these two is more robust across different paper and different tasks. Okay, so basically we designed a mechanism on top of this. We call this the generative peer prediction mechanism, GPPM. And later on, we realized that it actually works better. What works better is GSPPM, what does that mean is we can condition all some superficial information. Just like before, like in the previous example, this Z is the language model generation. But in this case, this Z can be like, for example, the abstract of the paper. The intuition of this is that abstract is sort of serves as a synopsis that the correlation between Xi and Xj about the abstract are actually not the desired information we care about. Those are very superficial information within the abstract of paper. So we really want to remove this. Okay, so this is a GSPPM. And then we run this on a clear data set. We do have a lot more experiments, but let me just show you one. So on the clear data set, we use Llama 70B model as the textual predictor. So you're gonna prompt Llama to predict another response. And then we use GPT to generate reviews. So we're gonna use Llama to estimate the GPT's review, how informative its GPT reviews is. And let's say we have two versions of them, 0.5, 3.5, which is an older version, and a more advanced version, GPT-4. And this p-value here is basically measuring how well this score that we're computing from the method can distinguish the human textual responses from the AI textual responses. So high p-value will be the case where these two distributions are very separated. That is a very good case for a mechanism because it can well distinguish real human information from the superficial AI generation. But a low p-value will be a case where this distribution is very similar. Okay. So for the evaluator, the higher the p-value, the better, because it can better distinguish information. But for the AI perspective, the lower is better, because this AI can generate textual responses that are more similar to human. Okay, then let's take a look at this bar chart. What we observe is that compared with GPPM, GSPPM can better separate the simulated response reviews from human reviews. And compare with the left-hand side and right-hand side, you can see that GPT-4 actually can generate more reviews that are similar to human. And they're both mechanisms. Okay, why is this cool? This GSPPM can serve as an automatic AI benchmark for tasks like review judgments. So we do have experiments on like Yelp review other than the conference peer review. And it can measure the ability of AI. And there's no concern of data leakage because the peer review data can be refreshed every maybe month or maybe a couple months, depends on the conference. And also it's manipulation resistant. So the only way that you can increase your score is to provide the judgment that are correlated with human. And that's the theoretical guarantee of this method. Cool. I'm going to pause here for questions.
Oh, for the IPI overload data, so did you assume that all the data is the human?
Good point. We do assume that, and we choose the 2020 year as way before the rise of ChatGPT. So we assume that's a more like human effort. But that's a good point. Right now we have maybe 50% of reviews written by AI. Okay. If no question, let me proceed with the last piece of project, which is decision-making under noisy peer review. And this part has less to do with AI, but more is a theoretical modeling problem. Let me recall the pipeline that we have reviewers generate reviews and conference has to make a decision on that. But in practice, it's a little bit more complicated because the data that reviewers provide come from the authors who submit their papers. And authors actually are agents with a different incentive. And here, what is troublesome about this is that the acceptance policy can affect or incentivize authors to take different actions. So when we make decisions using an acceptance policy, we should anticipate the strategic responses from the authors. Okay. Let me first motivate the problem. So how big is the problem? So this figure is a number of summations every year from the following past 5 years. As you can see that this year's AAAI also almost have like 30,000 papers. Like I would say this is like exponentially increasing. But the problem is that the decisions are really noisy. So there have been well-known Europe's experiments a couple of years ago showing that when we divide the decision committee into 2 parts and they are making independent decisions, but only 50% of them are overlapping. Another key problem about conference review is resubmissions. So when the paper rejected by a conference, the author can immediately resubmit it to a different conference. So for example, this 29,000 here of AAAI, a really big part of them actually rejections from Europe's this 25,000. So what's the problem here? This is a problem that community cares a lot. There have been a lot of discussions on how to improve conference peer review. But let me draw your attention to one comment, which is why don't we accept more papers or even all papers? Okay. What's the rationale behind that? It's actually pretty reasonable because when we are looking at one conference every year, 75% of papers are rejected, right? Only 25 are accepted. But if you look at the rejected papers, where are they going? The author is going to resubmit them next year or maybe same year, different venues. And then because the review noise, another 75% of this might be, or maybe lower, might be rejected, and so on and so forth, until the authors resubmitted a lot of times, eventually, a lot of these papers actually are eventually accepted with only minor differences. So why don't we just accept them sooner in this resubmission pipeline so that we don't have to read them many times, right? Average resubmission comes with 4 or 5 more reviews per paper. Okay, so this is actually a pretty plausible idea. But in this section, I'm going to show you why this is probably not a good idea. Let me walk through a model. So let's say we have a lot of authors, and there's only one prestigious conference. The quality of the paper is a scalar, let's say a real value, sample from some prior. The author make a binary decision about whether to submit to the, let's say, the prestigious conference or just to take a sure bet or offset option. So for example, the sure bet could be just like putting the paper on archive or submit to a second-tier conference. The prestigious conference has a acceptance policy that determines the probability of acceptance, and then there's a value for the author, which is basically proportional to the average quality of the accepted papers. And this scheme is repeated. So after rejection, the author will take the same decision next time, whether to resubmit or to take the sure bet, until it's accepted either by the prestigious conference or by the sure bet. But this is timely discounted, so modeling that authors prefer sooner acceptance than later. Okay, let me focus on a very simple setting to just like pay more attention to the specific idealized setting. So let's say the paper quality are real values, and review noise is an additive term. So review signal will be S equal to quality plus some zero mean Gaussian noise. And then the conference is going to draw a memoryless threshold policy. So that means every time the conference will sample one signal, review signal S, and then accept the paper if the signal is larger than some threshold tau. So if you look at the distribution of signal distribution, then the gray area will be the probability that this paper is accepted in this round. Okay, pretty straightforward. And we assume authors are noiseless, meaning that when they face many rejections, they won't change their belief because they know their underlying quality Q. So that means that basically, if my paper has been rejected many times with very negative reviews, I'm gonna be consistent in believing that my paper is a good paper. So under this idealized setting, we actually have a clean equilibrium result. Show that author's best response is another threshold determined by theta. If the quality is larger than theta, the author will submit and keep resubmitting the paper until acceptance. Otherwise, the author immediately take the shortcut. Okay. And this is quite interesting because there's usually a misalignment between the ideal threshold tau and the actual threshold theta, which is author's threshold. So let's say what is in the gray area about tau would be the paper that the conference aim to accept. But actually, what the paper that eventually turned in will be determined by the threshold theta, which we call this the de facto threshold, reflecting author self-selection. So in the end, the paper in the blue area will be the paper that eventually accepted by the conference because author is gonna resubmit and eventually get in.
Submitting or at some point they may give up on something else.
Oh yeah, because of this theorem here, and the authors are nonetheless, they will resubmit. They will always resubmit. There's a rational decision for them to always resubmit. And that's exactly why the threshold theta is gonna determine the paper that eventually accepted. The gap between tau and theta is kind of interesting. We call this the resubmission gap. And it turns out that there are a couple of factors that affect this gap. And I will show why this gap is important later, but just keep in mind that a more attractive conference, like a higher conference value or higher utility for acceptance, or a more patient author, or noisy reviewer will all contribute to a larger resubmission gap that will mismatch your tau and theta larger in these three cases. Okay, so now is the time to explain the resubmission paradox at the beginning. Why do we have to reject a lot of paper every year, but eventually they all accepted? Why don't we just lower the acceptance threshold and accept more papers sooner? The reason is that when we reduce tau and try to accept papers sooner, we also reduce theta, meaning that we are encouraging more authors to submit. And even worse, those papers in the purple area here are actually those papers that are more lower standard. Previously, they decided to quit because of all the self-selection, but now because you're lower tau, you're encouraging those others to submit. So basically, we are creating the same problem, just at a different threshold. We're not reducing the review burden because the distribution of papers changed. So here, the policy that not anticipating a strategic distribution shift will result in misalignment that the intended outcome is the same paper, but lower review burden. But actually, we have different batch of paper, not necessarily smaller review burden. Okay. Let me produce a little bit more insights on this. So now I'm gonna talk about what should the conference do in terms of the review policy to achieve better objectives. So what is the conference objective? It aims to accept more good papers and reject more bad papers. To do so, you have to draw a lot of reviews, right? So only when we have 1 million reviews for each paper and we make the perfect information about the quality of the paper, we can maximize this objective of accept all good papers and reject all bad papers. But there's a drawback of that, which is the increased review burden. So what is interesting about this is that there's a trade-off between these two objectives. We cannot obtain perfect conference quality with very small review burden. There's always a trade-off. So the lever of the trade-off is the acceptance threshold. for different threshold, we're actually altering this trade-off in a way that we're going to talk about soon. So let's define conference quality as the sum of all accepted papers qualities, and visualize that in the distribution. Let's just say that this is the paper quality distribution, and then everything about theta will be accepted. So the conference quality is essentially the blue area. And the review burden will be modeled by the number of reviews solicited for each paper during this resubmission process. So that will be the area about theta, but is weighted by the color, where the color here represent the number of rounds the paper is rejected before acceptance. So you can see that borderline papers are experiencing more rounds of rejection. So the review burden, they're contributing a lot more to the review burden than the high quality paper. Then varying the threshold will change the quality burden pairs. Like if I lower the acceptance threshold, accept more papers, the integral of this two terms will be different. But if I raise the threshold to very high, basically nobody eventually are submitting or accepted. We are basically accepting the top paper. And in that case, the review burden will be small, and the quality is also kind of basically zero. Cool. So a key question is, we're interested in what factor will lead to a dominating QB trade-off, meaning that under setting 1, can we achieve the same quality with a strictly less review than setting 2? Then we see setting 1 is QB dominating setting 2, and because you can always achieve the same outcome with a smaller review. It turns out that the factor that determines the QB trade-off is the smaller resubmission gap. So this means that I'm going to skip this part, but basically the conclusion here is that a smaller resubmission gap will lead to a better QB trade-off. And there are a couple messages building on this. So first, we show that the conference should be aware of the misalignment between the decision policies, the decision threshold, tau, and theta. And ignoring the strategy reporting of others will lead to misalignment. And second, because of this result, we show that a better review quality can benefit all stakeholders, like the conference, authors, and reviewers are all happy with a higher review quality. And the third one is actually more interesting, which is there have been suggestions of that we should reduce the review period from maybe 4 months to 2 months. But this is very dangerous because it's shrinking the cost of a resubmission. And because of that, we're going to have a larger resubmission gap and then a worse QB trade-off because by doing that, authors are trying to game your mechanism more often. Okay. So that's the end of this section. Any question? Okay, let me briefly sum up with the future direction that I think is pretty interesting. It turns out that we have been chatting about incentive alignment and policy alignment. And incentive alignment deals with human, policy alignment deals more with AI. It turns out that these two frameworks are somewhat similar. Like we aim to design an evaluator and reward to incentivize human. On the other hand, we can use the same thing to design a loss function to supervise AI. And there are many properties or similarity between the settings. For example, here we only have noisy peer data to evaluate human reports. On the other hand, we have noisy training data. And on the left-hand side, we have the multi-agent system. On the right-hand side, we have multi-AI calibration setting. And then the left-hand side, we focus on mechanism design. But on the right-hand side, we focus on the calibration framework. So the key insights is that the theoretical insights and empirical performance from both sides can be shared. Like the literature behind these two frameworks are very large, but there are less connection between them. So one kind of interesting future direction is whether we can map the theoretical insights from for example, incentive alignment literature to design better AI. and whether the nice performance of this AI technology can inform us to better incentivize human in a human-AI collaboration framework. And I believe there are many open questions here. Okay. That's the end of my talk. Thanks.
Any questions? Any questions? I'm sorry.
Yeah, I have a question. So I see some that could be a paradoxical statement there, right? Because you want the AI to be more human, and then you want to differentiate them. So is that two directions contradict each other?
So what I mean is like we want our objective
of AI is to make it more and more intelligent, look like human.
Yep.
And your perspective is from the opposite direction. You want to differentiate those things. So when the AI become more and more intelligent, maybe it's really hard. It's become harder and harder to differentiate.
Yeah, that's a very, very good question.
Paradoxical things.
Yeah. So basically, I think when that day comes, we no longer need human anymore. As long as there's a text that we still need human, there should be some gap between human and AI that we can still make AI do better. And basically, my discussion here focusing on assuming that we still have this gap and how to carefully or reliably measure this gap and evaluate it. But I think that's basically I'm a big believer of that. One day we will no longer need human data that much.
Yeah, I guess one thing I'm not expert in this area, but one thing that puzzles me is that if one day all the data is just produced with AI, we want AI to mimic humans, right? Would it still be AI, or I mean, wouldn't it hallucinate or something if it keeps reinforcing its own product in a loop and things like that? So that's why I think that the more we use AI, AI will probably do worse. I don't know.
Yeah, so like the question is, if eventually every step of this training pipeline are like we are taking more roles from AI, will eventually that mess up the system, like AI is reinforcing its own kind of data, right? That's definitely the good point. Like the example of the crazy call example where we do observe this happening in the beginning stage of when we train AI. But right now, people are more careful about this process. Like directly using AI data is like not usually a good idea. What they actually do is, so for example, they can aggregate different AI signals to a better one, or they can filter out some weaker AI. But basically, the key thing here is people develop benchmarks, which is measure of performance. And right now, basically, people are heading for making the performance on benchmark better. As long as it's better, it doesn't matter whether you are using AI data or human data. But at a higher level, I do think there might be a concern where a lot of data, like AI data, is on the internet, and a future version of the language model might be a problem. But let's see if it happens actually like that.
So my opinion about that question is, if you still evaluate AI with like human evaluation metrics, then there never be superintelligence. Because your human evaluation metric limit the power of AI.
Yeah.
But that's very dangerous.
Yeah, exactly.
Dangerous for that.
Yeah, might be the best thing you can do is like the average human. That might be the case. Yeah.
The evaluation metric will limit
the
capability
exactly.
of